Mhm. Okay, great. Thank you. You saved us some time. We can move on to the next speaker, I guess. Thank you very much. I'm sure there might be some questions coming up to the Q&A, and it'll be great for you can actually type your answers. Thank you.
I don't see any right now. Yeah, thank you.
Okay. Right. Now, I guess time is almost up. Yeah. So, okay. The next speaker is Dr. Tuomas Koskela at UCL, and the talk is about developing high-performance particle filtering software. Tuomas, if you are ready, please go ahead.
Thank you very much. Can everyone see my slides?
Yes.
Okay, good. So this talk is maybe going to have a slightly different focus from the previous speakers, but let me start by introducing myself. So my name is Tuomas. I'm a research software developer at UCL, and we're a group under the Research IT Services, and we work with research teams who want to create high quality software for research. And so I'm not an expert on data assimilation by any means, but I'm helping the group of Serge Gias to develop some software for the research. And I'm going to talk a little bit about that because I think all of us in this field work with developing our software, and perhaps you can use some of these things that I've learned in this project during your work. So we're working on a project called RADDISH, which is the aim is to couple agent-based models with physics-based tsunami models to simulate emergency evacuations, and both of these models include data assimilation. And I'm focused on the tsunami models part, and we're trying to develop fast implementations of particle filter codes targeted at HPC systems. So performance is very much our thing, and writing code that can run in parallel on large systems. So we're working on a particle filter for the tsunami model, but the aim is to be flexible so that you can experiment with different models, different filters. We've started by using very simple models with a linear tsunami model that's developed by some Japanese collaborators, and it's just a regular grid absorbing boundary linear model, and it generates from the same model some synthetic observations and uses analytic and initial conditions. So there's very little data being used, and we've developed a bootstrap particle filter, and this link down here is the link to our repository. You can go and have a look. So we've developed a bootstrap particle filter with Gaussian process noise, and then we're working on an improvement to a optimal particle filter, which is mostly the work of Alex Beskos at UCL. So I forgot to mention, so this project is a collaboration between UCL, Leeds, and Cambridge. So we want to talk a little bit about the technologies that we're using for this. So like you saw, so from the links where we're using GitHub to collaborate with our collaborators, and in particular, what GitHub is very useful for is for combining work of different authors through pull requests and code reviews. The second logo on the screen is for GitHub Actions, which is a continuous integration platform within GitHub, and that has been very useful for us for testing that the code that people merge is correct. The third one is perhaps the most interesting one. So we're using the Julia programming language, which for those who are not familiar is a language that is it's fairly new. It's been around for around 10 years, and it aims to combine high performance of like C and Fortran type with fast development that you would experience in Python or MATLAB, for example. And it does this by compiling the code just in time before you run it. It also has a very, very healthy package ecosystem, kind of like what you have in Python, and it has a very well integrated package manager that allows you to easily reuse code that has been written by others, which makes it very powerful. For the high performance, we looked at what our options are, and then in the end decided to use MPI, which is basically what everyone has been using for the past 30 years. The advantages of MPI is really that it works very well on HPC systems with schedulers, and Julia has some projects going on for different distributed parallelism, but they were not mature enough to be useful at this point. Julia does have built-in support for threads, so for like on-node parallelism, we are using threads from Julia itself, and we're using HDF5 for I/O, which is pretty much standard at this point. So I'm going to very quickly talk about the particle filter algorithm. So the general workflow is something like this. So you start at the top, you update your particle states, you add some process noise, you get true observations from your system and synthetic observations from your particles, and using these calculate particle weights. Then you, based on the weights, you resample your particles and perhaps do some like data collection to produce output. The nice thing about this is that all the sort of parallelism happens in this resampling step, and everything else you can do in parallel, sort of extremely easily. So I want to go through with how that resampling looks, because it's not as simple when you go to really high levels of parallelism. So in this example here, I have just 4 ranks which are doing the thing from the previous slide. So they're updating the state, which is X here, and then they're calculating the weights, which is W. And then what you need to do for the resampling is you need to do a global gather of all the weights to be able to calculate the distribution function. And then you can do a resampling of those weights, but you need to do it you need to have all the weights in one place. So the idea here is that the particle states may be so big that you can't collect them. You don't have enough memory, but you can collect the weights because they are just one number. And then you get some list of indices of what your new resampled particle should be. And you can send these out, and then all your ranks can then start sending particles back and forth to where they need to be after the resampling. And if this looks a bit messy, it's because it is. But then after this copying step, you can again reduce from your new particle states some statistical quantities like a mean and a variance. So these blue boxes here on the right are sort of the communication steps that you need to take. And those are basically the things that will end up hurting your scaling. So here's some results from the scaling of our code. This is on the Cambridge CSD3 system on the KNL partition. And I'm using, so sorry if this is a bit confusing, but on the x-axis I have the number of MPI ranks I'm running, and each node on the cluster has 4 ranks. So this goes up to 64 nodes, which is not crazy, but it's already quite a lot of parallelism. And then on the y-axis I have is the parallel efficiency. So basically 1 means I'm scaling perfectly, and anything below 1 means I'm losing some efficiency. And you can see that we're kind of, as we go to larger scale, we're losing a bit of performance, but we're around 90%, so it's not too bad. And this is so our particle states in this example have a 30,000 elements in each of them. So moving them around is already gets quite expensive. So you can sort of, if you wonder what is causing this loss of parallelism, here is so the x-axis is the same, but now I have on the y-axis the runtime of different components in the code. And you can kind of see that the particle state update, which is in blue here, is scaling perfectly. So is the noise. And the things that are slowly creeping up, which means taking longer time, are this MPI gather operation, and the broadcast would look the same, but I collected this on the master rank, which doesn't see the time spent in the broadcast. And then the reduction operation to produce the output. So this is kind of a feature of the algorithm as I've shown it. There's if someone is aware of optimizations, I'm very interested to hear about them, but this is the best we've been able to come up with. So to finish, I want to talk a little bit about the lessons learned that I had in the title. And the first and really important lesson, I think, is using continuous integration. So this allows you to test your code all the time. And especially when you have multiple people working on a code, this is really important. You don't want to introduce bugs without noticing them. So I strongly advocate starting early with continuous integration. And I apologize if this is obvious to everyone. Also, if you're writing parallel code, don't forget to do tests in parallel. This exposes a lot of interesting bugs. And using open source libraries is very useful, can save you a lot of time. Quite often someone has already done the stuff that you're planning to work on. And if you find something and it isn't quite right, don't be afraid to contribute. So open an issue, say, hi, I'd like to do this. It would need these changes. Can we work together? This is usually very possible. The next point is about interfaces. So the goal of this project, like I mentioned, is to produce models that can be coupled together to model evacuations. So interfaces between models, between data assimilation schemes, so on, are very important to have clearly in mind. And this is maybe something that we didn't do quite well enough in the beginning, and we're kind of doing some of that now. So the thing about using a high level language like Julia or Python or MATLAB is that it hides some of the more low level stuff like memory management, for example. But we've found that for performance, it's very important to be aware of where your memory is being allocated, even if you don't see it. And sometimes it happens in places where you wouldn't expect. So doing in-place modification has sped up our code a lot. And the last thing is maybe obvious for anyone who works with MPI, but beware of load imbalance, especially in a thing like a particle filter where you have a very unbalanced communication scheme when you're copying states around. If you're getting poor performance from a MPI collective, usually the reason is load imbalance, but you just aren't measuring it explicitly. So with that, I'm going to finish. Thank you. And yeah, feel welcome to have a look at our code. It's a work in progress, so be a bit careful and get in touch if you get interested. Thank you.
Thank you very much, Tuomas. I don't think we have received any questions about your talk. Maybe you explained it very well.
Takes some time to digest.
That's true. And myself is not very familiar with this. So in your model, what does each particle represent? What is defined as a particle?
So each particle represents a state of the model. So it's I mean it's like an ensemble basically. So the model is defined on a mesh, like I said somewhere that it was 100 by 100, and each particle contains the state on the whole mesh.
I see.
And then as you so basically you have observations at some finite number of points, and you assign weights to the particles based on how well they match those observations, and then you resample to keep the ones that match the best.
Okay, great. So very general treatment.
Yeah, I mean, yes. So my background is in physics with particles, and I found this confusing at first. This naming convention, but
okay.
Yeah.
Okay. Thank you. So yeah, time